We left off at question 18.30, which asks us to predict the product of this reaction. We have a benzene ring. We've got a nitro group on it, which is a strong electron withdrawing group. And then we also have two halogens, one at the meta position and one at the para position to the electron withdrawing group. And we have a methoxy, which is a strong base, but it's also a strong nucleophile. So strong nucleophile. And so we are set up for an SNAR reaction. However, you would remember the SNAR reactions will occur when we have a strong electron with group and we have a good leaving group like a chlorine or a bromine, but it has to be at the ortho or para position. And so the substitution will occur where the chlorine is. Let's draw the mechanism, and I'm going to draw an abridged version of the mechanism. So I'm actually going to redraw the starting material. I'll draw it right here. Okay, so what's going to happen, and the reason why I'm going to redraw is so I can draw out the entire nitro group, because I want to show the lone pair going into the nitro as where the nitro acts as the reservoir for the electrons, okay, from the nucleophile. So what happens is the methoxy group, I'll redraw that here. So here's our methoxy group, our nucleophile. So we get the nucleophilic attack occurring here at this position. And then we're going to push all of these arrows over here to show, again, that nitro group acting as that reservoir for the pair of electrons. So we end up with our bromine here. We have our methoxy group here. I'm kind of running out of space, aren't I? There we go. And we also have our chlorine here. We have our nitrogen, which has two bonds to oxygen. And both of the oxygens have the negative charge like this. So there's our intermediate. And then what's going to happen is now we're going to lose the leaving group, the chloride. So I'll use my blue pen. And we're going to push those electrons. We're going to restore aromaticity. And we're going to lose the chloride. And what that's going to give us is the final product. Right? Don't believe me, just follow the arrows. And then with a new double bond here and here, we end up with a double bond to our oxygen. And we still have this single bond over here. So, oops, getting ahead of myself. So here's our nitro group. And now we have our methoxy. And we ejected the chloride. So there's the product. Oops, I left my bromine out. But this is the product of the reaction. So if you just want to draw it without putting the entire Lewis structure of the nitro, this, we have the bromine here, and then we have our methoxy group here. There you have it. The next question says starting with benzene. So we're going to start with a benzene molecule and anything else that you can think of, okay? It says complete the following synthesis. Well, if you remember, we have no way to install a hydroxyl onto an aromatic ring. Okay, this is called para-aminophenol. There's no way that we have to install a hydroxyl in a ring unless, in terms of retrosynthesis, we were to think about having this molecule, right? If we had a nitro group here and a leaving group here, right? Then we could treat that with sodium hydroxide, right? And then we could do our SNAR reaction. So we'll say sodium hydroxide and heat. So that means we need to make this compound, parachloronitrobenzene. Well, we're going to start by installing the chlorine because the chlorine is an ortho-para director, whereas the nitro is a meta director. So let's put the chlorine in first, and then we can direct the nitro into the para position. So let's start by putting our chlorine on first. So we'll use chlorine and aluminum chloride. I could use iron too. Anyhow, I'm going to end up with chlorobenzene, which would be this. Then I'm going to install my nitro group using nitric acid and sulfuric acid. And I'm going to make parachloronitrobenzene. Nitro, like that. Next, I'm going to do my SNAR reaction, so sodium hydroxide and heat. And keep in mind, this is your SNAR. And you could practice drawing the mechanism if you want to. I'm not going to do it, but remember, we have the requirements. We have the strong electron withdrawing group. We have a good leaving group, and it's para to the electron withdrawing group. So let's draw product. So now we've got para-nitrophenol, this compound. And what's the last thing we've got to do? We've got to reduce that nitro group. Sorry, did I miss a step in my SNAR reaction? I think I did, because I end up with a phenoxide, don't I? So let me just move this over here. There we go. And I'll move this over here. And I'll move this over like this. There we go. So step one, of course, is sodium hydroxide and heat. And step two is hydronium. And then in terms of the heat, in the book it always says 70 degrees Celsius. Just writing heat is good enough for me. There we go. So the last steps are going to be the reduction. First step, to treat it with iron or zinc and HCl. And then in the second step, we treat it with base. And that's what I was thinking about. Getting ahead of myself. All right, there we go. So we've got our nitro group installed, and we have our, we have our amine after the reduction, and then we have our hydroxyl group here, like that. So how many steps is that total? It's a total of 6 steps, isn't it? All right, not a trivial number of steps. Anyhow, so that covers section 18.13, which is nucleophilic aromatic substitution, or SNAR reactions. And now we're going to look at the last reaction that's covered in chapter 18, the last new reaction, which is elimination addition. So remember that an SNAR reaction is not going to occur if the if the ring doesn't already possess a strong electron withdrawing group, right? The reason there's no reaction here is because you don't have a nitro group here, right? Or you don't have a nitro group here. You've got to have one of those in order for the reaction to occur. However, scientists can never stop, at just heating something at a moderate level. They always have to see what happens if you jack up the temperature to some crazy level. So if you heat this reaction to around 350 degrees Celsius, that's a lot of heat, my friend. You actually see that there's a reaction. Okay, so you take your halobenzene, so in this case chlorobenzene, treat it with the base at 350 degrees Celsius. Again, that's really high temperature. And then that would produce the phenoxide, right? You'd end up with the phenoxide since you're in base. And then in the second step, you treat it with acid and you produce a phenol. Well, this isn't an SNAR reaction. This is not a nucleophilic substitution. This actually occurs by an elimination first and then an addition. Let's take a look at how that happens. So the reaction works even better and doesn't require a high temperature if a stronger reagent is used. So instead of using something like sodium hydroxide, if you use a stronger base like amide, so this is sodium amide in liquid ammonia, you can see that works pretty well. So there we go. We do another substitution of that chlorine with an amine, again using sodium amide. But what's interesting about this is if you investigate the regiochemistry, you can tell that this reaction doesn't proceed through an SNAR mechanism, because if we have a methyl group, let's say para to the chloro, and you do this same reaction, so same conditions right here, you actually end up with a mixture of ortho and meta substitution. So sorry, para and meta substitution. So again, this tells you that the amide doesn't just come in, and do just a plain old SNAR. It doesn't happen that way. Okay, there must be something else. And that something else is first an elimination. So if you use an isotopically labeled substrate, it's clear that the substitution is occurring at 2 different carbons. So this is just more proof of what's being shown here. And an isotopically labeled substrate means you simply take the molecule and you replace one of the carbons, the carbon that has the chlorine attached to it. This is carbon 14. Okay, carbon 14 is a radioactive isotope of carbon, and so it can be easily monitored. Okay, so we have our carbon 14, and then if we try the same conditions, what happens is you see that the nitrogen is attached to the carbon with the carbon-14, but it's also next to it too. And it's about a 50-50 mixture. So this suggests a totally different mechanism that involves the formation of an intermediate that, yes, it's called benzyne, not benzene, but benzyne. Remember that "-ine" is the suffix we use for an alkyne. Now, if you're looking at the molecule, the structure of benzyne, and saying, Mr. Dion, that's insane, okay, or that's crazy. Well, hold on, we're going to talk more about the structure of the molecule, but the concept still stands that if the amide behaves as a base and does an elimination, so this would essentially be an E2 reaction here. Actually, the way they have it drawn is an E1, isn't it? But anyhow, we have the elimination of the chlorine. First, you abstract a proton, and then the carbanion that's formed is going to eject chloride, right? So you lose chloride, but then you end up with a triple bond in a ring. And again, I know that the geometry of an sp hybridized carbon has to be linear, and we're going to address that in a second. Okay, so nucleophilic attack by the amide can take place at either carbon of the benzyne. So once you formed the benzyne after the elimination, right, that was the first part, to go from benzene to benzyne, that's the elimination, okay? Elimination. I think I'm getting tired here. Elimination, that's the first part, okay, that we already looked at. Now the amide can act as a nucleophile, and it can attack either of these carbons, right? It could attack the radio-labeled carbon, but it could also attack the other carbon that isn't radio-labeled. And that shows you why after a proton transfer, right, you would end up with a mixture of both of these compounds. One where the nitrogen is attached directly to the radio-labeled carbon, and one where it's next door to it. Okay, so that proves the elimination addition mechanism, the fact that we get these two regioisomers with that radio-labeled carbon. So here's the mechanism, right? The first step is going to be the proton transfer, followed by the loss of leaving group to produce the benzyne intermediate. So that's the elimination portion. So all of this here, this is the elimination section. And then the nucleophilic attack, followed by the last proton transfer. Okay, all of this, that's the addition section, okay, or the addition portion of the overall mechanism. You need to know this mechanism. It's not a complicated mechanism, but it's very different than some of the things that we've looked at in this class so far. So going back to the benzyne molecule, now again, if you're thinking, well, it's impossible to have a triple bond, right? You can't have sp hybridized carbons in a ring because their bond angle has to be 180 degrees. But the thing is, if you try to make some benzyne and you put it in the presence of furan, which is this guy here, which is locked in the S-cis conformation, you actually end up with a little bit of the Diels-Alder product. So that is some evidence of benzyne formation. I'm not a benzyne expert, but one of the chemists or one of the professors in the chemistry department at UCCS actually is a benzyne expert. He did a lot of work on benzyne and research on reactions that involve benzyne as an intermediate. So our textbook goes into a little more detail on the benzyne, and it kind of addresses the whole bond angle situation here. And I'm not going to go into any detail because it probably won't ask you a whole lot about it. But they said it's almost like it's a diradical in a way, you know, and the unpaired electrons from this last pi bond are kind of in these sp2 hybridized orbitals, you know, unpaired like that. So sometimes it's, you know, treated like a triple bond. Other times you can kind of consider it like a diradical. And that explains why it's so reactive. You know, if you have a diradical, I mean, it's going to react like stink, right? Anyhow, well, let's look at the last problem. I think it's, no, maybe it's not. No, it's not the last problem. The last problem in this section, anyhow, that I have in the slide deck, it says, draw both products that you get when you take 4-chloro-2-methyltoluene and you treat it with sodium amide, followed by treatment with water. So let's start by drawing 4-chloro-2-methyl